Okay. So we're delighted to have Jeremy Quastel from the University of Toronto in our seminar today. Welcome, everyone. Jeremy actually is a former colleague of mine here at UC Davis, but that's a sufficiently long time ago so that all these beautiful things that we now know about KPZ and KPZ Universality were just a dream back then. There has been tremendous progress in this area, and Jeremy is responsible for much of it. And so I'm really looking forward to his talk. Take us towards KPZ Universality, Jeremy.
So thanks a lot, Bruno. And thanks a lot for the invitation to all the organizers. So I'm going to talk about recent works with my collaborators who are here. And of course, this will be mostly from my point of view about the KPZ universality. So, so the plan of the talk is, so I'll try to, I'm not assuming everybody knows what the KPZ universality is. So I'll try to give you some ideas about that. And then in the second section, we'll talk about how one of the models in the class called TASEP, we can solve it. And because we can solve it, we can pass in the limit to the universal strong coupling fixed point of the class. And then at the end, I'm going to talk about some very recent results, which were posted on Monday, about convergence to this KPZ fixed point of various non-integrable models. Okay, so let's get going, and let's talk about first this this picture you're seeing behind you. So this is an off-lattice Eden growth model. So you can think of it as a model of a bacterial colony, and these little balls, which are floating around, sitting there in 2 dimensions, are giving birth to new balls on neighboring unoccupied sites at some rate. That you shouldn't worry too much about the exact dynamics here, but you can see the new births as the pink ones on the boundary. Okay, now as this thing grows, well, because of the spherical symmetry, of course, it'll start making a ball. But what we're interested in is the fluctuations of the boundary. So if we sort of look in some direction, you can look and you can kind of imagine a height function over this northeast to southeast to northwest line, and in the northeast direction, you've got a height function. You have to be a little imaginative to see it's actually a function, and the thing's growing at some rate, a constant times t, because you've sort of made time so that the whole thing's growing, essentially at a constant rate. But the universal thing here is these fluctuations of the boundary. So you've got this strange exponent that the fluctuation of the height is this t to the 1/3, which is very unusual, and then it lives on a scale of t to the 2/3. This is all for large t, and you see these universal processes, which I'm calling here a of x, as the fluctuation of the boundary. So a of x is supposed to be this function one might actually see here, and these are the things we want to capture, and these things depend on how you start the thing. So if you started it instead of from, well, you can imagine this picture was started from one seed in the middle, but if you started it from a half space, you would have the same thing, except the A would be a different universal stochastic process. So these stochastic processes A are special stochastic processes just defined through their finite dimensional distributions. Their finite dimensional distributions are given by certain determinants, and we'll see that later. And we want to understand how they come up and what they mean. Okay, so what I'm talking about it should be very, very universal in 2-dimensional models like this. I'm only talking about 2 dimensions. There may be similar things in higher dimensions, but we have essentially no ideas. So for example, just to show you how universal it is, you could have a random metric, which is sort of given by these colors. And you could take balls in the random metric. It's supposed to be a homogeneously random metric on this flat space, and then you take balls in the metric, and the balls again, they sort of are of size some constant times t, and then the fluctuations, which should be exactly the same universal process that you saw in the previous picture. And these kind of conjectures have been verified a lot in simulations, and well, there's some rigorous work, which I'm going to show you. But definitely for the models that I'm talking about, there's absolutely nothing proved. I'll start to tell you when things are proved and not just conjectures. So I could show you a dynamic simulation on a computer of the thing, but it's more fun to show you this little movie, which might as well be a simulation of fluff burning in a park in Spain. And the fire front here, not all fire fronts should be KPZ, but this one sure is. You can see that the front looks very, very similar to the type of things you saw in the previous pictures. And in fact, it absolutely should be. Okay. Okay. So the type of models which I was talking about, we have absolutely no access to because you don't even really know what the height function is. You saw that in the first slide. It's a little bit hard to even define anything. So all the work is on directed models. So in directed models, we're basically just going to set it up so that the thing is a height function, perhaps over a one-dimensional lattice. Okay, so now we're in 1 + 1 dimensions instead of 2. Okay, so ballistic aggregation is the most famous and first studied of these models. So in ballistic aggregation, we have the integer lattice, and over the integer lattice, there's heights of blocks. And the dynamics is that blocks are falling from the sky, and they're falling independently at every site, say as a Poisson process. And then they pile up. But if they just piled up, the process would be essentially trivial. You'd know everything. But in this model, there's one little twist, which is instead of just piling up over the lattice site where they're dropped, they stick to the side if there's a side there to stick to. Okay, and so that produces a strong nonlinearity into the dynamics. Well, let me show you what it looks like on a large scale. You can see that stuff is not just growing up, it's growing outwards. And that's the key effect you see in this ballistic aggregation. So now we've gone to a directed model, but again, this ballistic aggregation, although there have been enormous amounts of numerical studies on it, because it's fun to put on a computer, we essentially haven't the slightest idea of anything about ballistic aggregation. The main problem being that we don't actually know what the invariant measure of ballistic aggregation is. Now, to study this model ballistic aggregation, Carter, Pergy, and Zhang introduced a stochastic partial differential equation, which is supposed to encapsulate the main effects there. Okay, so there's 3 key things driving the dynamics. So now, first of all, we've got a height function. Although there's a picture down there, which is a lattice picture, the height function is now a function taking continuous variables over the real line. So it's a function h of t and x, and everything are real numbers now. Okay, so the time derivative of h has 3 things driving it. The first is a space, well, the first to the right here is a space-time white noise, which is supposed to encapsulate the effect that the particles in the ballistic aggregation were dropping independently at every site and in time. Okay, and so you can just think of the space-time white noise as randomness, which is uncorrelated in space and time. And then there's a relaxation term, if you just had dTh equals dx squared h, you would have the heat equation. So that smoothens the interface and keeps it an interface. And third, you have this key term, which is the lateral growth term, which is a nonlinearity, it's a quadratic nonlinearity of the slope. So what does that mean? Well, if you look at this little picture down here, oh, decided not to. Okay, there it goes. If you look at the, sorry, go back. If you look at this little picture, the lateral growth is, so this thing is growing outwards, as I said. And of course, the vertical component of growth, which is what dTh is supposed to be, is a nonlinear function of the slope. Well, you can see that from the picture. You might try to calculate the nonlinear function and tell me that it's not just the square of the slope, but there's a kind of magic in this equation that it doesn't matter what nonlinearity one actually has. And you always see a quadratic term. So the only nonlinearity is a quadratic here. And if you started with something else, you can kind of check that you would arrive at the same equation by a kind of renormalization that happens in the equation. Okay. So again, in this equation, we're supposed to see the same thing. We're supposed to see that the thing grows at rate a constant times t. Here, of course, we started from, you can even see here that we started from a flat interface at the very bottom. And with fluctuations of size t to the 1/3, and they're supposed to live on this scale t to the 2/3. Now, in the KPZ equation, you have a simplification over the ballistic aggregation that you actually know what the invariant measure is. It's Brownian motion. So if you start with the Brownian motion, you stay with the Brownian motion. And if you look on a smaller lateral scale than t to the 2/3, all you'll see is Brownian motions after large time. So it's important to zoom out. We'll see that later to get non-trivial processes. So, but of course, all these non-trivial processes are locally Brownian motions. All right. Okay. So, so we're supposed to see this, and I'm going to write it in a slightly different way. I'll have a small parameter epsilon, and we'll look at this rescaled height function, epsilon to the 1/2, h of epsilon to the -3/2 of t and epsilon to the -1 of x. And that's just exactly the same thing as saying that the fluctuations, the epsilon 1/2, is the 1/3 of time, and the lateral fluctuations are the 2/3 of time. So it's just another way to say that. And what you expect here is that as epsilon goes to 0, you should see interesting things. These are supposed to, this thing should converge to these universal lateral fluctuation processes, which I was describing on the first slide. Now, Kbz equation itself is rather hard to make sense of because the h's look like Brownian motions locally in x, and so dxh squared is a rather hard object to make sense of. And of course, most of you know that that problem was solved by Martin Hare, for which he got a Fields Medal. But that kind of theory, which is a small time, well, finite time theory about the KPZ equation, telling you that it makes sense, is not something that you can use to probe the very large scale phenomenon that we're looking at here. So we're trying to look at the long time large scale behavior of the KPZ equation. And this will converge to this strong coupling fixed point, which I'll talk about in a second. But you won't see things like that from local well-posedness theories. Okay, you need different tools. So the big tool here is a special model. Oh, I'm sorry. So there's going to be some surprises. And the big surprise, and so this is just to whet your appetite for what's coming later, is that so let's just suppose that I look at the one-point distributions. So the one-point distribution here, which is the epsilon scaled, height fluctuations at a single x point, and because I started with flat, it doesn't matter what x I take. So that's a function f of T and R. T is the rescaled time, and R is just the distribution function variable here. So it's a function of f and t and r, and its second log derivative satisfies the Kbz equation. So why is that? so that's a big surprise, and the answer is I don't have the slightest idea why it's true. It's a physical law which is derived in a very strange way by an enormous algebraic computation, which I'm going to try to show you. So we really have no idea, and it's not something one can relate to old derivations of KdV for water waves and things like that, because at the scale of Kbz equation, you can't have an equation like this for one quantity like this, the one-point distributions. All the multi-point distributions will satisfy some sort of hierarchical equation, very coupled, and you don't see anything like KdV anywhere. So it's a big mystery how this comes up or why. Okay, but let me tell you the story of how it does. Okay, so the story comes from this model TASEP. So TASEP is a very special discretization of the Kbz equation, or you can just think of it as another model in the class. It's very simple to describe, and I'll do that now. So the height functions now live over the one-dimensional integer lattice, and the rule about the height functions is they can only go up or down one from each lattice point to the next. So one of these height functions is drawn here, and it's called a simple random walk path, which just says the same thing as what I just said. You can encode the height function in particles just by drawing a particle, the little blue particles down below, wherever the height function goes up. So you can either think of the thing as particles or the height function. There's one little thing here, which is that the solvability, which I'm going to describe in a second, wants there to be a rightmost particle. This doesn't seem to bother us too much, but it's just a fact of the algebra. Okay, so the height function just goes down after a certain point, but that point could be far, far, far away to the right, so it doesn't matter too much. Okay, so here's the dynamics. The dynamics of the system is that a little local max will jump to a little local min at rate 1. And every little local max is doing this independently of the others. And when a little local max jumps to a little local min, it's the same thing as a particle jumping to the right, but the jump only happens if there's no particle in the way. So let me just show you. So little maxes jump to little local mins, little local max jumps to little local mins, and you can see the particles jump with the thing. So you can either think of these particles performing what's called random walks with exclusion, with jumps just to the right. That's called the totally asymmetric simple exclusion process, or the height function jumping down. Okay, so that's the whole dynamics. It's very, very simple. And you can perhaps ask what on earth this has to do with the Kbz equation. It's not too hard to see that when one of these little local maxes jumps down, so the rate of jumping down is just -2, because when you jump down, the height function drops by 2, times the indicator function that there was a little local max there. But algebra with functions which only take the values plus or minus 1 is kind of fun. And if you just calculate -2 indicator function, there's a local max, you can just write it as a half times the backwards gradient of h. That just means h of x minus h of x minus 1 times the forward gradient of h of x plus 1 minus h of x, plus a discrete Laplacian of h, and then minus 1. So basically, TASEP is just a discrete version of the Kbz equation. It's not a discretization which converges to the Kbz equation. It's just another model in the universality class, kind of parallel to the Kbz equation. If you want convergence to the Kbz equation, you have to do something slightly differently. You could allow jumps up instead of just jumps down. So let's go back. So if you want convergence to the Kbz equation, you could have jumps up and jumps down. If you had jumps up and down at the same rate, then you would have something called the symmetric simple exclusion process. And the interface just fluctuates back and forth, and we'll talk about that in a second. But if you put a slight asymmetry in the rate, which is to take the asymmetry as epsilon to the 1/2 as you're rescaling the way I showed you before, but in diffusive time, I'll show you that in a second, then it will converge to the Kbz equation. Okay, so that's the connection between TASEP and KPZ. Okay, and here's a picture of what it would look like if you started TASEP with a wedge initial data. Wedge initial data obviously just means this black line. So there's all particles to the left of the origin and no particles to the right of the origin, and you let the thing go. And then after a while, it looks like this blue line. And well, you can see this universal processes, which we were talking about in the first slides. And again, it's supposed to be the same process, and you can prove it is. Well, oh, sorry, you can actually derive that process and then conjecture that it is the same thing in the first few slides where we don't have any information. Okay, so here's a sort of big picture of what's going on in this business. There's lots of models in this universality class. So this is supposed to be the space of models, a kind of ill-defined enormous space, including all sorts of things. And in this universe, there's some special solvable models, TASEP and its friends. There's some variants of TASEP called push TASEP, discrete time TASEP, all of which will have the same solvability. And then there's models which don't seem to have much solvability, and we only know by sort of simulations and generalization, sort of saying, oh, it must be the same, which are models like this Eden models that I showed you in ballistic aggregation. First passage percolations, that's FPP. Or for example, I think this audience will appreciate, if you had a dynamic easing model with two phases, and you put on a magnetic field to favor the phase which was a blob in the middle, then it would also, supposedly, the boundaries would grow in the same way by this KPZ fixed point. But if you didn't have a magnetic field, if you just had a boundary separating two phases in again, always in two dimensions, that boundary without the magnetic field would just sort of fluctuate back and forth, and it would just look like the symmetric simple exclusion process I described before. In the universality class, there's two fixed points. One is the one up top. The interesting one is the universal KPZ fixed point, which we're trying to probe. And down below, there's another fixed point, a kind of trivial fixed point, which is the Gaussian or Edwards-Wilkinson fixed point, which is what you'd get if you just had that symmetric model where the thing just fluctuated back and forth. And it's just a linear stochastic PDE. It has a slightly different scaling, this epsilon 1/2 h of epsilon -2 epsilon -1x. So there it's a 1, 2, 4 scaling, whereas we're looking at this 1, 2, 3 scaling. The two fixed points have different symmetries. The Gaussian fixed point is symmetric either under taking the height and flipping it to minus the height, as you can imagine from the symmetric flipping model I described, or reversing time. Whereas the KPZ fixed point is skew time reversal invariant, which means that if you flip time to minus time, you also have to flip the height to minus the height to preserve the thing. And that's true about several of the models in the class, like TASEP. In TASEP, this is kind of obvious, just if you just think of the dynamics. The Kbz equation itself, which is written in the middle here with the yellow line, is the conjectured unique heteroclinic orbit joining the two fixed points. When lambda is 0, you have the Edwards-Wilkinson model. So lambda equals 0 in the Kbz equation that's what the Edwards-Wilkinson model is. And as lambda goes to infinity, you're supposed to go to the Kbz fixed point. So we try to prove all these things. Okay, so here's the the solution of TASEP. Okay. So I'll talk about where this came from in a second, but this is the formula for the transition probabilities of TASEP. And this is true for any initial condition. So we have our initial condition here, which I just wrote with blue with some peaks in it. And then at time t later, I'd like to know the probability that the height function is something. Well, we know that the way we should describe a random function is by writing down its finite dimensional distributions. So I take m spatial points x, and I ask what's the probabilities that the height function at those spatial points is less than or equal to ai's, and that's given by a determinant. It's a Fredholm determinant of I minus some operator that you compute out of the initial data and the t's and the x's and the a's. Sorry, the t and the x's and the a's. So let me just quickly go through these things. There's a matrix Q, which is nothing but the oh, and sorry, this determinant is being computed on L2 of the positive integers. Okay. So there's a matrix Q, which is the transition probabilities of a geometric random walk jumping down. That's what Q is. And then out of this Q and your initial conditions, IC, you produce a operator or a kernel, depending on your preference, RIC, which is just the identity minus essentially the transition probabilities for a geometric walk to stay below your initial condition and go from some point to some point. And those 2 points, the point that you started with and the point you ended with, are the variables inside the kernel for our IC. So our IC xy is x1, x2 would be the probabilities for a geometric walk starting at x1 to x2 to stay below the initial condition. And you do roughly the same thing for the final condition, except there's a sort of duality and you want to stay above the final condition. The Q's being from the geometric kind of walk. Okay, so this is the formula. It's a kind of surprising formula. So let me just tell you where it comes from. So the formula is not the first solution of TASEP. So TASEP was actually solved by Schutz in 1997. What Schutz did is he gave a formula for the probability that n particles starting here end up in these n positions at time t later. And it's an n by n determinant. And the entries in the determinant are sort of complicated contour integrals. I won't write the formula because it's not much more than that. You won't be enlightened. That formula was derived by beta ansatz. It's a rigorous derivation. And the problem with that formula is that's not sort of what we really want, because we want to pass to the large time scale limit. And so what we really want is to start with an enormous number of particles and then ask where just a few of them are at time t later. And that would involve integrating out a lot of the ladder variables out of this formula. And that's not something so easy to do. Actually, that problem was solved by Sasimoto in 2005, who realized that, well, first there was a result by Johansson. So if you have wedge initial data, then there's some toplet structure in the Schutz formula. So he was able to study it with that. But the way you study this formula is very, very heavily dependent on the initial data. But what Sasimoto realized is that there were certain functional relations in these contour integrals which allowed you to rewrite Schutz's formula as a signed determinantal point process over a space of what's called Gelfand-Zeitlin patterns. And what that allowed them to do, Sasimoto and Borden and the others, was to turn the problem into a completely different looking problem, which is you're given a bunch of Charlier polynomials. So Charlier polynomials are just orthogonal polynomials on the positive integers with respect to the exponential distribution. And you're asked to take these Charlier polynomials and then shift them in a certain way by the initial data and ask for their biorthogonal pairs. And this is a strange problem, which there was no real method to find the solution of that. They were able to solve it in the flat case, essentially by guessing, but it didn't go much beyond there for 12 years until, by studying the sort of form of what the KPZ fixed point should be, we were able to guess, and then the proof is not that hard, what is the general solution of that biorthogonalization problem, and that gives you the formula I wrote on the previous slide. Once you have the formula for TASEP, well, one has forward and backward equations. It's just a Markov process, and you can check that that formula is just the unique solution of the forward and backward equations. So once you have the formula, it's not that hard to check later that it's correct. Okay, so that's the history of the formula. It took about 20 years to solve TASEP in a form where one's able to pass the limit. Now, when you pass to the limit, there are these mediating operators in the formula, which involve exponentials of t times negative gradients. The negative gradient operator is just the one I told you before. It just takes a function f to f of x minus f of x minus 1. And then these q's, but it's actually q's are being taken to negative powers. And it turns out that the q, which is the transition matrix of a geometric kind of walk, is actually invertible. So you could just write the formula like I've done in the middle here. And then in the scaling, what you discover is that the thing cancels not just to first order, but also to second order. And so the sort of generator, if you like, of the processes becomes this g cubed operator. So Kbz is actually a world in which the normal probability, which is Brownian motions driven by d squareds, is replaced by d cubes. And then the initial and final conditions where something had to avoid a geometric quadrant walk had to avoid the initial data just becomes a Brownian motion having to avoid the initial or final conditions. And so now I can give you the formula for the KPZ fixed point. So just passing to the 1, 2, 3 scaling limit, and the previous formula was set up to do it. One gets the exact formula for the transition probabilities of the strong coupling fixed point of the universality class. Okay, so here the Markov process is evolving functions on over the line. The functions are continuous functions. In fact, they have the same continuity as Brownian motions, and they look locally like Brownian motions. And just like Brownian motions, they're defined in terms of their m point distributions. So if you start from some h0, you would like to know the probability that at time t, at m points, it's less than or equal to m given values. And you won't be surprised that that's given by a Fredholm determinant. This is just a limiting formula of the TASEP formula. It's a bit prettier in the limit. So the determinant is a determinant of an operator k, which encodes the initial data and the time and the x's and the a's, and is being calculated on the m-fold product of L2 of 0 to infinity. Okay, so the important thing for us about the k's is that you take your initial data, and out of your initial data, called h0 here, you produce a kind of pre-operator kh0, which encodes the initial data. And once you've done that, and you're living up in operator land, or kernel land, depending on how you like to think of it, the evolution is completely trivial. It's just a conjugation by this exponentials of d cubes and then d squareds to tell you where you're looking. Those give you the positions of the particles, and then d's to tell you what height you're looking. And so you can see immediately, of course, that the fixed point is a completely integrable system. And the only thing I should tell you is the Brownian scattering transform, which starts with an H0 and produces for you this KH0. So the scattering transform is described just below with the picture and the p hit. So you take your H0, it's a function over the line. It doesn't have to be as nice as the H0 here. So for example, the wedge initial data, because you've been scaling and the wedge turns into a wedge which looks like this. So it's natural actually to look at upper semi-continuous functions. And so since they're upper semi-continuous functions, a function's upper semi-continuous if it's hypograph, which just means all the stuff at or below the graph, is a closed set. So we'll talk about hypographs of functions. Okay, so the transform's defined as follows. So starting from U1, we take a Brownian motion or a Brownian bridge going from U1 to U2, and we ask what's the probability that along the way it hits the hypograph of H0. And that's called p hit, and we do that in a finite interval minus L to L. And well, you could ask if p hit actually defines for you the function H0. It's an operator. Well, it's not obvious, but actually it's true that if you know p hit, you know H0. But we're interested in more because we want to actually have H0s on the whole line. So we have to try to take some limit as L goes to infinity. And as L goes to infinity, it's sort of clear that what I just told you has to be false, because the Brownian motion, if you try to scatter off of something with a Brownian motion in the middle, as L gets large, it's going to get too blurry to actually produce the function H0. So what this odd thing tells you to do is to solve the heat equation backwards around p hit and take a limit as L goes to infinity. And that's your KH0. And now you can ask if that makes any sense, because you're not supposed to solve the heat equation backwards. But as long as t is positive, so it's not actually true that that limit makes sense if t is 0. But if t is positive, the d cube mollifies the thing enough that you can check that the total operator actually makes perfect sense. So it's been written a little bit informally here, but the k, depending on t, actually makes perfect sense for any t not equal to 0. And in fact, this map from H0 into kt for t not equal to 0 is a continuous bijection from upper semi-continuous functions into the trace class. Okay, and so that's the formula for the KPZ fixed point. And with this formula, actually, you can just start differentiating the n-dimensional distributions in T or X or A, and you discover the following thing. The fixed point can also be described by a bunch of integrable PDEs. So of course, as I've written at the top here, the finite dimensional distributions. So here we have the n-dimensional distribution of the fixed point at time t. These n-dimensional distributions for every n would define the fixed point for you, and they satisfy the following integral with PDEs. So the log derivative of the f turns out to be the trace of something which is the solution, or its derivative is the solution of a matrix version of the Kbz equation, which is a known integrable PDE. I think, looking at this crazy equation for Q isn't going to be very enlightening, but if you take the n equals 1 case where things are a little simpler and you don't have to go through this mediating matrix Q, because it's just the trace of a 1-by-1 matrix is pretty easy. So if you look at the 1-point distributions, so that's just f of t and x and r, and you take its second log derivative in r, that thing satisfies the classic KP equation, which is written there and is just a spatial generalization of the Korteweg de Vries equation. So people think of it as the 2-dimensional Korteweg de Vries equation, and it's integrable in the same way as KdV. And so that's the extra x, which you would have if you didn't start with flat initial data, but you actually had x-dependent initial data. Then it would satisfy this equation instead. This is also like KdV, a soliton equation, but it appears that the type of data that we have here, which is completely different than anything anyone studied before, will not develop solitons in any of these equations. Okay, and this again shows that the KPZ fixed point is an integrable Markov process in the sense that its transition probabilities are a completely integrable system. Okay. There's a third description of the KPZ fixed point, which I'll just go over quickly. For each fixed time t, you can think of it as a solution of a variational problem, similar to, well, exactly a noisy version of the Laxo-Leinik formula for the Burger's equation. Where this noise, AXY, is a 2-parameter noise, which we call the Airy sheet. And the thing is that this Airy sheet, unlike the KPZ fixed point, is not something we know very well. It's not true that we know what the process AXY is exactly. We don't have a formula for its finite dimensional distributions or anything. If you freeze one of the variables x and then look at it in y, then it's just that universal process I showed you on the first slide, the Airy process. And if you fix y by symmetry, it's the same thing in x. But the joint behavior in x and y is not so well known. But we do know now from a recent result of Duncan Novern and Balint Virag that AXY is a well-defined unique object because there's a special last passage percolation model. It's actually a sort of last passage percolation model built on what's called the Airy line ensemble, which is another determinantal process. And you can define AXY as a strong limit on that process, which means it's a functional on that process. But it's not a very direct definition, though it gives you some geometric information. Okay, so those are that's what the KPZ fixed point is, and happy to answer any questions. It was a bit fast, but I'd like to go on in the talk and talk about the next problem, which is that we have some solvable models. So now we want to talk about some universality. What we'd really like to do is prove that lots of models converge to this KBZ fixed point. So we have the solvable ones, and we can prove those converge to the fixed point by solving them and getting a formula for their Markov transition probabilities and taking a limit, and we get these transition probabilities of the KPZ fixed point. And then there's these partially solvable models, like ASEP, which is the ones which flip up and down, or things like what are called the 6-vertex models, or these completely not solvable models. Kbz equation itself, I would classify as a partially solvable model. We have some formulas for KPZ for 1-point distributions starting from a few special initial data, but that's sort of all you have there. And that's the same sort of thing we have for 6-vertex or WASEP. It doesn't look like one's going to get general formulas in those cases. And then in the not solvable ones, we don't have any formulas at all. So the question is, how are we ever going to prove convergence of anything to the KBZ fixed point except by solving the model? So the history is that there was big efforts from about 2000 to 2010 on these solvable models, and then from 2010 till the present on these partially solvable models. But the basic idea there is that you find a formula, sometimes after enormous effort, and you take its limit and you get these special formulas in the KPZ fixed point. The most typical case is that you start with this wedge type initial data and you get the GUE Tracy-Wynnum distribution. Now the GUE Tracy-Wynnum distribution in my language from the previous slides is just a special self-similar solution of the Kbz equation. You can check that with the symmetries of the wedge initial data, the KP equation has a special self-similar solution, which is given by certain panel of A transcendents, and that's the thing we call the Tracy-Wynnum GUE distribution. And similar for the GOE distribution, though, for example, there wasn't even a rigorous formula for the KPZ equation starting with flat initial data. It's only one or two initial data that we know. So the thing I'd like to talk about in the last couple of minutes is that this past summer, a few blocks away from each other, Balint Virag and Sourav Sarkar and I independently found proof that the KPZ equation converges to the fixed point, and we mean for general initial data and multi-point distributions. And the two proofs are very different. Both start with the fact that because we know a lot about tightness of the KPZ height functions from work of people like Alan Hammond and Ivan Corwin, we really only need convergence on a dense class of initial data. So Balint's using some fantastic symmetries of last passage percolation models and an approximate version of the variational problem I showed you. Of course, that's a restriction because the model will have to satisfy some approximate variational problem and have those symmetries. And it seems that so far it definitely requires some solvability in its model. So our method, which I'm going to show you in the next 2 minutes, is based on energy estimates. It's an analytic method, and at least we can do it for one definitely not solvable model, which is finite range exclusion processes. So in finite range exclusion processes, it's just exactly the same as the TASEP, except that the particles are allowed to jump over each other. They're still not allowed to jump to a place where there's already a particle there, but they can jump 25 sites if they want. So you make some jump law, and that's your model. And of course, the height function now sort of goes up and down in blocks. Okay, we can't do it for any initial data, but we can do it if we randomize the initial data a little. So let me just explain the method. So the method's based on a very, very simple idea of how you would compare two Markov processes. So we've got two Markov processes defined through their transition probabilities. So P sub I of HGB is the probability that in process I, starting from H at time T, you're in a set B. And the processes have generators, and the generators in this case just tell you how these P's evolve according to the Kolmogorov equation. And we might as well just assume that mu is the invariant measure of both of them. Okay, we also have densities which evolve sort of dually to probabilities. So FITH is the probability density at time t of your height function. That's a density with respect to the invariant measure. And they evolve according to, dt of f is L star of f. Okay, so now the formula, which is sort of highlighted in the middle here, is that if you look at the difference of the two transition probabilities, then here I've sort of generalized a little bit. Instead of starting with an H, I could start with some probability distribution, which I'll call F0 d nu. So Pi F0 d nu is the probability starting with F0 d nu, and then at time t, you're in some set B. Okay, so one can just check, and I wrote the proof there, but actually the formula is simple enough that if you thought about it, you could write down a proof in a few seconds. This is just given as an integral of the evolving forward density of the second process and the difference of the generators acting on the transition probabilities of the first process, integrated in time and over nu. It's a very simple formula. I'm sure I've never seen it before, but I'm sure people knew this formula, but it probably just never had any use before because if you have two processes with the same invariant measure and you sort of look at large time and ask what's the difference, well, they're both supposed to be in the invariant measure. So it's not a very, the problem would normally not come up, but here, because we're scaling out, the invariant measure isn't what you're going to see. You're going to see these interesting processes. Okay, so we'll take P1 to be our TASEP, and just to show you the method, I'll take P to be the asymmetric simple exclusion process, which has only nearest neighbor jumps, but I'll tell you how to modify it for non-nearest neighbor jumps. And we'll compare it to TASEP. Well, if you look at the probabilities of TASEP and ASEP, just using the formula, the difference of the generators of TASEP and ASEP just turns out to be symmetric simple exclusion process. So so that symmetric simple exclusion process, because of the way the generator is set up, it allows me to integrate or sum by parts and write down the difference as a kind of a Dirichlet form, where these grad x's are just the operator which tells you what's the difference of a function before and after a flip. Okay. Okay, so how are we going to use this formula? Well, what the formula is telling us is that if we're able to calculate grad xp's and grad xf's, we might be in some shape. Well, we have a formula for p TASEP, so grad xp is something we can calculate. So the question is what we do with grad xf. So that's the energy method. So the same formula is written on the top here from the previous page. And so what you do to try to get information about grad xf is you just differentiate the L2 norm of the evolving density of ASEP with respect to the invariant measure. Well, that's an easy thing to do. And you just find out you get minus the Dirichlet form. The L2 norms contract. This is just a general fact about Markov processes. And the contraction rate is the Dirichlet form. But that tells you something. That tells you if you start out with a bounded initial L2 norm, then the Dirichlet form is bounded by that initial L2 norm. And so we could just use Schwartz inequality in the top formula to get a formula for the difference of TASEP and ASEP in terms of the initial L2 norm of the density and the Dirichlet form of P TASEP. But as I said, P TASEP, we have a formula for it. So we can calculate grad x of P TASEP. And if you take your set B to be the kind of sets which we're interested in, which is the sets where a function h is less than some function g, so we have a fixed function g and that defines the set B, then you can just check that grad x of P TASEP is actually a probability distribution. It's the joint probability of the argmax and the max of sort of evolving backwards from g plus the initial h. Okay. Okay, so let me just quickly say what happens. If you just plug in P TASEP and calculate that thing, you find out that it's epsilon to the 3/2 and you learn absolutely nothing. And that's because this probability distribution is very intermittent. But the problem allows you to do some averaging. So if you average over the set B a little bit, which you can do because it just gives you a slightly fuzzy version of what you wanted, then that gets rid of the intermittency and you can check that this Dirichlet form of the grad x P TASEP is actually of order epsilon squared. And so that gives you an estimate of how far P TASEP is from P ASEP. If you accept that your initial data is a bit fuzzy and your B is a little bit fuzzy. But that's enough. And that lets you identify that, for example, here, ASEP converges to the same thing as TASEP, which means that we've proved that asymmetric simple exclusion converges to the KPZ fixed point. This is just a little picture to show you that you can find a function. You can find, if you start with an initial function, which is written in red, you can kind of Brownianize it by just dividing a little. You can show that uniformly it's close to a measure which has finite initial L2 norm on compact sets. Okay, so those things are dense. And the only thing I should end up with is to show you how does it work for the KPZ equation, how does it work for finite range exclusions. For the KPZ equation, we just take weakly asymmetric simple exclusions, and the thing tells you that by taking a limit, that the fuzzy version of the fixed point transition probabilities and the KPZ transition probabilities, after you've rescaled KPZ to be in large time, so delta is now your scaling to large KPZ time. I'm almost finished.
Okay.
And so this gives you a bound on the difference of those fuzzy things, which tells you that the KPZ equation converges to the fixed point. And for finite range exclusions, exactly the same method as ASEP works, except that you need a bound. You need to control, the key step that we used was to control the difference of generators by some Dirichlet forms. And that's an estimate which is called the strong sector estimate, which was actually proved by Xu and Baridan in the early 90s in hydrodynamic limits. So that estimate, just slight twist of it to include height functions, tells us that exactly the same proof works. Okay, so here's the papers which is written on, and thanks a lot for your attention, and I hope people have a few questions.
Thank you very much, Jeremy. Really wonderful talk, and the announcement of some next step, great progress towards KPZ universality. Are there any questions? So we will try to just unmute and ask a question. If it gets too busy, I will organize it.
I have a question, Jan Derezinski. In the last estimate, there was a number A. What was it?
Yeah, sorry, I was going quickly. I think you mean this one, right? The one at the bottom here. Or I might have been, the same thing maybe on a later slide, but let's just look at it here. Yeah. So it's a good question. Yeah, so I have to do a little average over shifts of my set B in order to have the thing become the right order. That little average, it better be little, or else I'm going to make too much error. So I don't want to make my set B too fuzzy. But when I do that average, basically that average comes inside the Dirichlet form, and then I have to use Young's inequality, and then you pay the price of the L2 norm of that convolution. So A is the size of the little average you did. So you pay a bad price for it, A to the -2, because you want A to be small. But you see, it doesn't matter, because what you do is you first let epsilon go to 0, and it tells you that for any degree of fuzziness, the TASEP and the ASEP are close. But that's enough information to tell you that they have the same transition probabilities.
Okay, the next question. There was a lambda in the KPZ equation. I mean,
yeah.
So what can you get rid of it, or?
Yeah. So to go to large time. So if you let's just put it. There we are. Yeah. So when you go to large time, you actually don't want the lambda. You don't want to let lambda go to infinity, because that doesn't quite make sense. So what you do is you rescale, so the lambda goes into the other part of the equation, the dx squared h and the xc. So basically, you rescale into lambda time, so you have dth. I hope you're seeing what I'm seeing. I'm looking at the middle equation here, the KPZ in the middle of the picture. So you rescale time in the equation so that in front of the dxh squared you have a 1. And in front of the dx squared h and the xc, you have lambda to the -1s. And then as lambda goes to infinity, lambda is basically the delta I was talking about later. So lambda goes to, sorry, 1 over lambda is the delta I was talking about. So you'll basically have a small parameter in front of the dx squared h and the xc, which are going to 0. And of course, you're sort of going to some version of the Hopf equation, dth equals dxh squared as the fixed point. The fixed point is just some kind of Hopf equation. Does that make sense? Did it answer your question?
Yeah. So the lambda is a free parameter in KPZ. You cannot remove it or.
Right. So as lambda gets large, the thing looks like this KPZ fixed point, and as lambda goes to 0, it looks like a Gaussian object.
Yeah.
Well, you could lambda goes to 0. You can do it for yourself just looking at the equation. Lambda goes to infinity is a bit harder, right?
Yeah. Another question: the Airy sheet. Does it have anything to do with the Airy equation, or where does the name come from?
Yeah, that's a good question. So whenever you have this let's look at back. Whenever you have this d cubed, so if you just look at this kernel e to the t d cubed, the fundamental solution of that is a rescaled Airy function. So all the formulas in the past were full of Airy functions. People didn't know where they came from. So you had a formula, for example, for the GUE kernel is just some sort of integral over Airy functions. So Airy functions were everywhere, and so when the process was first introduced, the one that I showed you on the very first slide in the curved geometry, the boundary, they called it the Airy process after those Airy functions. I think the whole thing's hilarious because Airy himself, he actually worked very hard to suppress the work of Korteweg and de Vries. So I don't think it's fair that he got his name on everything. It's the Airy sheet because it's a two-dimensional version of the Airy process, just like the Brownian sheet is the two-dimensional version of the Brownian motion.
Thank you.
And yeah, okay.
Okay, thanks.
Hi, can I ask a question?
Sure, go ahead.
Hi.
Hi, I enjoyed your talk very much. I was interested in the convergence of non-integrable models to the KPZ fixed point. And I was wondering how generally you can apply your method to other non-integrable models.
Right. Okay, it's a very good question. Well, the application to non-nearest neighbor exclusion was posted on Monday, so it's probably a little bit early to make any generalities. The answer is I don't know. It definitely uses an enormous amount about TASEP. I've certainly tried, and if I go to models which don't have certain symmetries of TASEP, then the calculation of grad xp doesn't give me things that I can work with. And so that's a problem. So that calculation of grad xp is very essential here. You're sort of throwing all the somehow the formula that I gave you, this formula coming up, throws the whole problem onto P. Actually, you can see it in the highlighted equation. You look at the difference of your two generators, and all you have to do is calculate that on P. You see, on P1. P1 being the P TASEP. And somehow F2, you don't need to know so much about it. So what's happened here is that because we knew that these models were sort of perturbations of TASEP, we got away with it, and it's not so clear how far it goes. But of course, it's encouraging.
So can I ask a related question? I'm sorry.
Oh, go ahead.
Is it okay? Yeah. So does this mean that these models, TASEP and ASEP and everything, have exactly the same scaling when you approach the scaling limit? So I naively imagine that you need some renormalization or something, but here you're just comparing the two.
So this is a very good question. And one of the other things which I'm using like crazy is this large renormalization constant, which can be tremendously difficult to calculate in various cases.
Right.
In TASEP and ASEP and finite range, I can calculate they're all exactly the same. Or at least, sorry, in finite range, I can match it to a certain TASEP. So you're quite right that I'm using that like crazy.
Yeah, is it a miracle, or do you understand the reason for this?
No, I understand the reason very well, and it's explained in the
Uh-huh.
paper. It would be
Okay.
a tiny bit hard to describe. If you write stochastic PDEs for them, you can see that the constant's going to be the same. It's not something I can explain in 1 second.
Uh-huh.
But you're quite right that if we try to go to more general models, unless you can calculate that big renormalization constant, which you can't accept in a few special models, you're not going to be able to use, that's a clear obstruction. Now, what the other obstructions are, there may be many more obstructions. I wouldn't promise it goes any farther than this right now.
Thank you. Yeah.
So I think we believe that all models showing the KPZ exponent do converge to the KPZ fixed point somehow. But can you?
Oh, that's not true. That's not true.
Oh, okay.
So there are fake KPZs. So for example, you can make a fake KPZ by conditioning Brownian motions to lie above parabolas, and produce fake versions of these things which do not converge to the fixed point.
So sorry, the initial condition is special, or what the time evolution is special? Where is the? Sorry, could you say again the definition of that fake KPZ model?
Oh, well, I have to think about it for a second. But so there's a lot of results about boundaries of blobs in Ising models, where you get exponents which are the same as KPZ, but the processes that you'll see are not exactly the universal KPZ processes. So it's not true that the thing's just defined by the exponent. So there are other things with the same scaling, but they're not. They're missing. They're missing certain symmetries which you would need to get the fixed point. So it's a little bit more complicated than you're saying. Of course, of course, if there's a certain number of symmetries in the model, then you believe that it should converge to the KPZ fixed point. Right now,
could you send me reference later? I mean, I will.
Yeah, sure. I'll find it and send it to you. But to some extent, what you're saying is true. The problem with the KPZ universality conjecture right now is it says that all models in the universality class should converge to the KPZ fixed point. But that's the definition of the universality class.
Right.
So right now the conjecture is a lot of models will converge to the KPZ fixed point.
Very good.
Thank you.
Can I ask?
Are there,
Yeah, I've got
yes.
probably a naive question, but you said that these higher nonlinearities could just go away; they could be ignored. But is there some possibility of fine-tuning which would lead you to other universality classes in some sense, a bit like multi-critical points in?
You can. So I don't know if this is exactly what you're asking, but if you took a quartic KPZ and then you tuned it badly, you would get into Edwards-Wilkinson.
Right.
But you have to be careful to get. So you have to be careful to get into KPZ class.
Right.
Yeah. Is that what you meant?
Well, sort of, but I wondered whether in the same way as in equilibrium stat mech, you could get sort of whole hierarchies of multi-critical points in some sense.
No. So it's not believed to be the case. So so definitely one believes there's only these two fixed points, and yeah. So we have a paper with Martin Hare where we prove, and then it was generalized later. Essentially, if you put any function there, when you just renormalize to make sense of the equation, you get quadratic KPZ automatically, unless things are tuned badly, and then the quadratic term just happens to disappear. But that's all that can happen.
Okay.
Are
Are there any other questions?
May I
Yes.
ask a question?
Tomohiro.
So this is
Go ahead.
Tomohiro. I'm still wondering about the question of Kazumasa about the kind of applicability of your method to show the convergence to for non-integrable systems to the KPZ fixed point.
Yeah.
So for example, so this point maybe you mentioned that. What about the initial conditions? For any initial condition, can you prove that each model goes to the KPZ fixed point? No.
No. So I'm sorry I went a bit quickly. For Kbz equation, we can prove that for essentially any initial condition, and I think we could prove for any initial condition. But that's using the fact that if we know, you have enough information to say that if you have a dense class, then that's enough for Kbz equation. For finite range exclusions, you don't have anything like that. So it turns out the big problem is that finite range exclusions are not monotone. So if you start with one height function above another, they don't stay that way. And you really need something like that to be able to prove you can go from a dense class to a to more. So for finite range exclusion, we're stuck with the statement I said, which is that if you start with a initial data in L2, then it goes to the fixed point with that initial data. And that such things are dense, but we don't know. So for example, if you ask me if flat finite range exclusion goes to GOE, I can't tell you right now.
Oh, I see.
I can show you something very close to flat, arbitrarily close to flat, which does go to GOE. That's my statement so far.
I see. So, but for ASAP, you can do basically the same thing as for KPZ equation.
For
right?
ASAP, you have essentially the general result. That's right.
Even for that case, for example, for the flat case, nobody has given a real proof, I think.
No, that's right. We got stuck at a certain point. So we have a formula for flat ASAP, but you actually can't prove that formula goes to GOE.
Method, you can prove
it. Now I can prove that flat
without any fancy formulas, you say.
No, with no formulas. Yeah, I know. It's kind of nice.
That's almost surprising.
After all that time fighting with that horrible formula. Yeah.
For me, it's still a bit surprising that you can really compare the general ASAP to TASEP, So I have been thinking that the TASEP is really special, and the ASAP is more, especially when it's pretty close to symmetric case. ASAP
if you think in terms of operators, it's not all that surprising, because if you think of the transition probabilities of just being the e to the t of the generators, it's kind of clear that the ASAP generator is just the TASEP generator plus a symmetric simple exclusion generator. And the symmetric simple exclusion generator, it's not being scaled right. It's just clearly going to 0. So formally, it's kind of clear. And all this is doing is kind of making that formal argument rigorous.
In a sense, also, in the opposite way, you could have done basically similar argument much earlier, right? Is it also true? Comparison of the ASAP generator to TASEP generator.
Well, to tell you the truth, I have a paper with Benedict Valco from 2006, where we proved that the diffusivity of any finite range exclusion has the same diffusivity as TASEP. So in the sense of a certain object called the diffusivity, and this is an equilibrium result, you get this t to the 1/3. And the method's the same
I see.
as here. So in a sense, it was done earlier. I guess it was, I think it might have been some trouble earlier because it wasn't so clear that even if we had gotten a certain point, this grad XP, you just sort of, you would be scared to compute it. It turns out it's not, it turns out you don't need the formulas to compute it, but you would have been scared to try.
Yeah, of course, after having understood a lot of formulas and KPZ fixed point, there has have been a much stronger motivation to do this. Yeah. I see.
Very good.
Okay, thank you.
If there are no other questions, nobody unmutes, then in fact we can